Okay, hopefully I am recording now and you can see my screen as well as me. We're going to use a PowerPoint file. I'm just checking it's recording, appears to be. So we're going to use a PowerPoint file, a little bit of OneNote, and basically I will be sitting here saying the things I would normally say if I was up at the board in the room. What you'll see on the desktop is pretty much what would be on the screen. And we're going to work our way through that, and then you guys are going to do some work. So we're introducing the topic of circular motion here. This is a hugely important topic. It's really interesting. It ties in with satellite motion and like the orbit of the Earth around the sun, with Kepler's laws, with Newton's laws. There's loads of stuff that follows on from this. It's really interesting stuff. And in terms of the exam, Leaving Cert, it's really, really important. So obviously things can move in a circle for loads of different reasons. Ferris wheels probably running off some sort of diesel or kerosene driven engine, a bit like a car motor. Electric turntables like washing machines, dishwashers, and the turntable of a record player. Gym equipment, loads of stuff. Objects in orbit, obviously. Tie something at the end of a string and just twirl it round and round and round. I'm trying to find the screen here. Twirl it round and round and round and round in circles. And you got circular motion, all for very different reasons. Gravitation, electric forces, mechanical forces. But what we're going to look for the moment here is we're looking at the maths that applies to anything traveling in a circle, regardless of why it is traveling in a circle. So let's take a figure skater. If you can imagine her, like just the tip of one of her fingers, if you think of that as the object that's in circular motion, when we can measure the motion in two different ways. We can measure its speed in two different ways. We can talk about linear speed, which is the traditional way that we've always talked about speed, distance over time, junior cert stuff, how many meters it moves per second, or we can measure its angular speed, what angle it moves through every second. If we think of something tied to the end of a string, like two weights tied to the end of a string going round and round and round in circles, if we look at the outside one here, that's obviously going through a bigger circle than this inside one. They'd both go through the same number of circles every second, so they'd have the same angular speed, the same number of radians per second, but they will be traveling with a different linear speed. The one on the outside is obviously traveling more meters per second than the one on the inside. The two measurements then, the key measurements we're going to be looking at here are linear speed and angular speed. Let's focus in on those for a second. V represents the linear speed. It's distance, speed, and time stuff from junior cert. Linear speed is distance divided by time. So here, if it's going around in a circle, the time it takes to travel from one point to the other. The arc of the circle is our distance L, in time T, V is L over T, measured in meters per second. Omega is how we measure the angular speed. Okay, I'm going to pause here. Okay, I'm back on, starting again. You may have noticed the mistake there that I've just quickly corrected. So we've agreed that linear speed, distance over time measured in meters per second, omega represents the angular speed, what angle it moves through each second. So if we look at the angle theta divided by the time t, the angular speed is theta over t. It's measured in radians per second, not degrees per second. Basically, radians are the standard measurement of how we measure angles, not degrees. This curly guy here is the Greek letter omega. Many students call it W. You can call it anything you want, but I will be calling it omega. Now, those two measurements, V and omega, linear speed and angular speed, are connected up by the equation V equals R omega. Linear speed is the radius multiplied by the angular speed. The derivation of that is interesting. It's one you need to know for the Leaving Cert. It's only a few lines long. It's very simple algebra. If we start with V equals L over T as our beginning point or as an axiomatic statement, the L is the length of an arc of a circle here, which follows the maths L equals r theta. Multiply the angle at the center of an arc by the radius, you'll get the length of the arc. So V is equal to r theta over t. We can just rewrite that. There's no mathematical change between these two lines. I've just put the theta over t inside a bracket because theta over t, we've just established, is omega. So we can replace the theta over t with omega. We've derived the formula V equals r omega. One you need to know and be familiar with for your leaving cert. Only a few lines long. Don't worry about learning anything off by heart for the moment. Another mathematical analysis of circular motion. Remember how waves have a frequency f and a period t? Frequency is the number of waves passing per second, measured in hertz. T is the time it takes for one wave to pass, one complete cycle to be completed. And those two measurements are connected by the equation that t is equal to 1 over f. The period is 1 over the frequency, or vice versa. Frequency is 1 over the period. Well, that applies to waves. It also applies to anything that's traveling in a circle. So if we have our object traveling round and round in circles, it has a period, the time it takes to complete one full circle or one complete cycle. It also has a frequency, the number of circles or cycles completed per second. And the same relationship applies between those two. T is equal to 1 over f. Let's look at the sort of maths that you would be expected to work on with this. So if we have circular motion, an object is in a circular motion with an angular velocity of 9 radians per second and a radius of 20 centimeters. What is its linear velocity? Now, I'm going to step out of that and try to work through this in one note. So we know here that we have omega is 9. The radius is 20 centimeters, which is 0.2 meters. And we're looking for linear velocity. So the equation we're going to use is V equals R omega. So R is 0.2 by 9. That comes to 1.8. It's linear speed. So it's meters per second. These are in the textbook. They're also in the PowerPoint that I'll be sharing with you. Now, vinyl records. Still around, I know, mainly what we call the 12-inch singles, 12-inch recordings now. Back in my day, you used to be able to buy the 12-inch. That was the LP. That was the full record, maybe 12 songs. Or you could buy a single song on each side of a smaller disc, what we used to call a 7-inch disc. 7 inches was the diameter, so radius is around 3.5 inches or 8.9 centimeters. So if that, and they used to spin faster than the 12 inches, they used to go at 45 RPM. They were often called 45s. Now, so what is the period of the motion of an old single going at 45 RPM? So we're looking for T. So I know that T is 1 over F, but I don't immediately have F here. F is the number of circles per second. What I know over here is the number of revolutions per minute. Essentially the same measurement, but in the wrong units. So we have to change the frequency from per minute to per second. So we divide by 60 and we get 0.75 hertz or per second. So the period, how long it takes for one cycle, is 1 divided by 0.75, which I'm going to round off as 1.33 seconds. So the old 7-inch single 7-inch disc used to take 1.33 seconds to complete one full circle. That's the first part done. We know the period. Next thing, what is the linear velocity? So always start with your formula. So if we're looking for linear velocity, the obvious formula is V equals R omega. I know the radius. We've just been told that the radius is 8.9 centimeters or 0.089 meters. Omega is the issue. So Remember how omega was theta divided by t, angle per second? Well, we know that if it goes through one full circle, it goes through an angle of 2 pi radians in one circle. And we've just established that that will happen every 1.33 seconds. So we can say that omega, 2 pi divided by 1.33 is 4.72, excuse my writing, radians per second. Omega is 4.72. So we can put that back in over here. 4.72 is now omega multiplied by the radius 0.089 gives me 0.42 meters per second. Let's go back into PowerPoint and have a look at those again. More neatly printed. So linear velocity, always start with the formula V equals R omega. You have R and omega sub in 1.8 meters per second. The vinyl records one, the period of the motion is 45 revolutions per second. Turn that, or per minute, turn that into seconds by dividing by 60.75. T equals 1 over F 1.33. Now this version here, T equals 2 pi over omega. It's variation on omega is theta over T. And it's essentially a formula you should be familiar with. T equals 2 pi over omega often is required to measure the period of anything. You'll get familiar with that when we see questions. And that comes to the 0.42 meters per second. Okay, that's my bit done. So your bit. So reread all of that. It shouldn't be very taxing. We are starting with baby steps here. That's page 203 to 206. Have a look at the questions on page 206. Really should take you, 20 minutes, half an hour max to do this. And I want that completed by Monday. I may start looking for some photographs of work done as a way of keeping track of this, because I know the temptations that can strike when no one is looking directly at your work. But I'm also going to follow this up with a short Isaac physics exercise, maybe only 2 or 3 questions, because I know I can follow that up very quickly. There are some Isaac exercises that haven't been completed yet. You know who you are. I might be sending some emails out. Please don't make me do that. So have that done by Monday. If you don't have your textbook with you, I can imagine how that might happen. All of the Edco books have been available for free online for the moment. So this could be textbooks even when you're not using revision guides. Everything are available using the codes shown on that slide there. I think Folens have done something similar, but I couldn't see their codes to hand, but I'm sure they could be found very easily with a bit of a quick online search. Okay, I'm going to post this. I'm going to post the PowerPoint that went with it. And as I say, your job, look at the questions on page 206, going on to 207. Obviously, it's 11 questions. They should be done by Monday, and I will email out solutions to those on Monday. Thank you. I don't know how to stop this.